day everyone, and welcome to this lecture series on the binomial theorem. This is the second last topic that we will be covering in the grade 11th math. We will go in this topic in a step-by-step manner. First we will talk about what the words binomial mean, and then we will look at the different types of uses that we have of the binomial expressions. And then I'm going to introduce to you the Pascal's triangle and how we can use the Pascal's triangle to solve for equations or basically expressions in which we have to deal with calculations that cannot be solved, that cannot be explained or basically simplified in a typical manner that we use for any other expression. Now, for example, now to begin with, in the beginning we have the binomial expression. So a binomial expression is the one which contains two terms. I think this is pretty straightforward if you look at the term binomial, and bi means two. So any expression that would have two terms is going to be called a binomial expression. Now we have to talk about binomial expansions in this lecture. How are we going to expand those expressions in which there is more than one term, and what are the methods that we use? Now, for example, if you have this expression over here, 1 plus x whole to the power of 0, this is basically going to be 1 because we already have done this in the I think you have already done this in the previous classes as well, that anything raised to the power 0 is 1, no matter what the magnitude is, no matter what the terms are. Anything raised to the power 0 is 1. Now if you go beyond that, if you have 1 plus x raised to the power 1, this is pretty straightforward. This is just basically 1 plus x. Now we have seen this next formula, that is 1 plus x whole square. Now this is going to be expanded in the way that we have already done. Basically it means 1 plus x being multiplied by 1 plus x, and we're going to get 1 plus 2x plus x square. I'm just writing the 1 over here because it is much more easier to explain. Otherwise you don't have to actually write this 1 over here. Now this becomes a bit tricky if the degree of the term is increased. If we have 1 plus x cube, now over here what we have over here in front of you basically is already a simplified version of the expression. We have 1 plus x, and then we have the expansion of 1 plus x whole square, that is 1 plus 2x plus x. But you see, in an exam or in real life, you're not going to have these simplifications with you. You might just have 1 plus x cube. What are you going to do then? Then you would basically have to basically simplify this in the way that 1 plus x would be multiplied by 1 plus x and then again being multiplied by 1 plus x. Now that is going to require a lot of calculations, but you see it is still solvable. You can still solve that. I mean, you would have to require like 5-6 steps, but still that could be solved. What if you go beyond that? What if you go in a higher power of this expression, that is 1 plus x raised to the power of 4? Now this becomes really complex. Over here in the example that you see in front of you, we have 1 plus x being multiplied by 1 plus x whole cube. Now this is, as we have it in front of us, is being used over here in this expansion of this expression. But what if you don't have this? What if in an exam you only have 1 plus x raised to the power of 4? Or what if you have a question that just find the coefficient of x squared? What is the coefficient of x squared in the answer? What are you going to do then? You would have to do all the calculations, 1 plus x being multiplied by 1 plus x being multiplied by 1 plus x being multiplied by 1 plus x. So you're going to spend a lot of time doing the calculations, and you might make a mistake here and there because more the number of terms, the more chances there are to make a mistake. And then all to get one term in the end, that is 6. So you see, when we have expressions like these in which there are two terms, but you're being asked to simplify them or expand them in the way as you can see in this slide, it gets a bit tricky and it gets a bit messy. And because of the calculations, we have a new method to solve this, and that method is basically called the Pascal's triangle. Pascal was a very well respected mathematician who came up with this approach to answer these sort of questions. Basically we are going to be dealing with the expansions of two terms, expansions of expressions that contain two terms. So you have the Pascal's triangle. Now let me first show you what the Pascal's triangle is. Now we are being expanding this. So this is what we have in front of you. This is known as the Pascal's triangle. Now the things to note about this triangle is that it is flanked by ones on the left and the right, and all the numbers in between are basically sum of the numbers above it. So 2 over here is basically a sum of 1 and 1. 3 over here is a sum of 1 and 2. 3 over here is a sum of 2 and 1. 10 over here is the sum of 6 and 4. 20 over here is the sum of 10 and 10. So you see, these are the two things that you need to keep in mind. Another thing that you can see is the symmetry. Basically, terms are being repeated in terms of whenever we are dealing with even number of terms, and the terms are once again being repeated with the center term whenever we are dealing with the odd number of terms. For example, if you see over here, you will see 1, 7, 21, 35, and then they are being repeated 35, 21, 7, 1. It's like a mirror image. If you have a mirror right down in the center, because there are 8 terms in this row, we will see that it is being repeated in this way. However, if there are odd number of expressions like the one over here, we have 1, 8, 28, 56, 70, 56, 28, 8 and 1. So in these terms, what you see is that you have an extra term here in the middle, and then it is being repeated 56, 28, 8, 1. You see, then it's a mirror image. So remember that whenever you are, maybe you're asked to draw a Pascal's triangle, maybe you're not provided with the Pascal's triangle in an exam, so remember these three things, that one is that it is flanked by ones on the left and the right. Second is that the terms are basically the sum of the terms above it, and the third one is the mirror images. That is just to confirm that the Pascal triangle you have in front of you that you might have to draw yourself is correct. Now, how does Pascal triangle help us in the expansion of the binomial expressions? So let's just say you have this expression over here, 1 plus 2x by 3 raised to the power of 7. Now it is pretty complex. It will get pretty complex because you have to multiply 1 plus 2x by 3 6 times, other than the one that you have in front of you. So what you do is that you use the Pascal's triangle to find out the coefficients of different terms. Now let me show you the answer first, and then we can relate it to the Pascal's triangle, and then we can do the next question after that. So the first thing that you see over here is we will only be talking about the coefficients that we are getting with the help of a Pascal's triangle. Now the way to use the Pascal's triangle is that you look at the power of the expression. The power of the expression is 7 over here. Pascal's triangle basically represents the power through its rows. So 0, this is row number 0. This will basically represent the coefficient of any expansion that is being done raised to the power of 0. As we have already discussed, anything raised to the power of 0 is 1. So if you have anything raised to the power of 0, you're going to get 1. If anything is raised to the power, if any binomial expression basically is raised to the power of 1, you're of course going to get two terms. Now those two terms are going to have coefficients of 1 and 1. Anything that is raised to the power of 4 is going to have coefficients of 1, 4, 6, 4 and 1. Remember that the first row represents power of 0, then the power of 1, 2, 3, 4, 5, 6 and 7. Now we have the question that we are being asked, that we have to solve for the Pascal's triangle. We are going to be asked for the coefficients of anything raised to the power of 7, which is going to be the 8th row of the Pascal triangle. Why would this be the 8th row? Because the Pascal triangle starts for the power of 0. Now let's look at the expansion that we have done of the binomial expression and see that whether it matches the expansion of the Pascal's triangle. So what are the terms that we have over here? The coefficients. So we have 1, 7, 21, 35, and then it is being repeated 35, 21, 7, and of course 1 is over here because you don't write 1. Now let's look at what do we have to do? Power of 7, that is going to be the 8th row of the Pascal's triangle. And how do we know this? How do we find this out? This is first row, second row, third, fourth, fifth, sixth, seventh, eighth. The eighth row is basically going to represent the power of coefficients for the power of 7. Coefficients for the expansion of any term that is being expanded to the power of 7. And what do we have over here? The same coefficients that we have in the answer. That is 1, 7, 21, 35, 35, 21, 7 and 1. So we go in this once again, confirm it: 1, 7, 21, 35, 35, 21, 7 and 1. So this is it. So in order to expand, in order to use the Pascal's triangle, in order to expand using the Pascal's triangle, this is what you have to do. You have to look at the power, then you have to look at the Pascal's triangle, and remember that you have to look at one row more than the power that you have, because Pascal's triangle starts with the power of 0. So starts with the coefficients of the power of 0. Now, this is the first thing that you have to do for the Pascal's triangle, expansion through the Pascal's triangle. But there are many other things that you have to do. Basically, two other things that you have to do. The two other things that you have to do require the expansion of the terms within this expression. Basically, the values of the terms that are going to be used in the expansion, because you see 1 is also being raised to the power of 7 and 2x plus 3 is also being raised to the power of 7. So the way to do that is that you see this as an a plus b raised to the power of 7 expression. When you would see this as an a plus b raised to the power of 7 expression, you would see that we have to first deal with a. Let's just deal with a. Let's forget about everything. So a is 1 over here. So in order to expand a, what we do is we start with the highest value of a, that is a to the power of 7, and then we start decreasing till the point that we get a to the power of 0. So we have a to the power of 7, then we write down a to the power of 6, a to the power of 5, 4, 3, 2, 1, and a to the power of 0, which will eventually give us 1 once again. Now since a is 1, that is why we get 1 over here as well. So this is one thing that you have to do. The expansion of a raised to the power of 7 and then being raised to the power of the expression and then being decreased accordingly step by step. On the other hand, as for b, what do we have to do for b is that we have to go in the opposite direction. We have to start with 0 and keep increasing its value by 1. For example, we have 2x plus 3 over here. In the first expression, what we're going to get is we're going to get 2x plus 3 raised to the power of 0. So once we have 2x plus 3 raised to the power of 0, in the next expression we're going to have 2x plus 3 raised to the power of 1, as you can see over here. Then 2x plus 3 raised to the power of 2, 2x plus 3 raised to the power of 3, 4, 5, 6, 7, till we go to the number of the power that we have of the expression. So basically, in order to expand any binomial expressions, you have to deal with three stuff. And one thing that you have to keep in mind that I'm going to help you, then that is going to help you expand this expression and help you with, especially with the signs of the terms used in the expansion. The first thing that you have to keep in mind is the expansion of a. How different values of a are going to what values of a are going to be there in the expansion. And the way to do that is that you start with the power of the expression and you decrease step one by one, you go all the way down to the a raised to the power of 0. Like we have 1 over here starting from 7 and going all the way down to 0 raised to the power of 0. Second thing you have to do is the expansion of b. Now b is, you're going to expand b in the opposite way. Basically b raised to the power of 0 and then b raised to the power of 1, 2, 3, 4, 5, 6, 7 and up to the point to the power of the expression. Now once you've done this, the third thing that you have to do over here is that is use the Pascal's triangle to find out the coefficients of all the expressions, all the terms in this expansion. Now we know that this is being raised to the power of 7. What that would mean is that using the Pascal's triangle, this expansion would have the values of the 8th row of the Pascal's triangle. The 8th row, why? Because the Pascal's triangle starts for the power of 0. The first one is basically the power of 0. So we look at the 8th row, which is this one, and then we put in these values. We take these values 1, 7, 21, 35, 35, 21, 7 and 1, and then we put it in these terms. Then we would have the answer to our question, that is the expansion of this binomial expression. So remember these three things: expansion of a, expansion of b, and coefficients. How do we find the coefficients? We find the coefficients by looking at the Pascal's triangle. The things that you have to keep in mind are basically four. A is going to start with the value of the power of the expression, go up to the and its power is going to decrease up till 0. B is going to start from 0 and go up till the power of the expression. Pascal's triangle, the thing you have to keep in mind for the Pascal's triangle is that it is basically the values that you have to take has to be one more than the power of the expression. And lastly, the thing that you have to keep in mind is the sign used in the expression. Over here, we basically using the plus sign, the positive sign, but of course we can get any term with a negative sign as well. And we're going to do that in the next lecture, and we're going to continue this one. So hopefully I'll see you then.